So today we're going to talk about looking at two independent samples. Last time we had a paired sample, so we had one measurement and a second measurement, and we ended up taking the differences because it was the same units or the same matched pair time, so you can correlate. In this case, it's two independent samples. A very typical way you would get data like an experiment. You randomize some people to control and some people to treatment. You get measurements of the control group, you get measurements of the treatment groups, and are these groups, are the outcomes different for them? Right? That's what we're going to look at. So sometimes this gets referred to as methods for two independent samples. We're focusing on means. The two sample, we'll use a t-distribution. So I sometimes abbreviate some of the notes like 2t, two sample, which is using the t-distribution. Right? So homework's due on Friday. That covers this and the last couple topics we did. On Friday, we'll discuss the exam 2, which is next Wednesday, so that's in a week. Right? Primarily cover the homeworks that we've done since the first exam. We'll talk about which formulas to know, what's the scope of it. There'll be some practice problems. Monday will be a review day to go over more problems, talk about things. No homework due that week, just focusing on the exam and reviewing stuff over the last few weeks. Okay. So last time we had one example with the museum artifacts, right? That paired thing, right? Who would do a study like that? So in the Burlington Free Press, the next day, there's an article about putting plants in patients' rooms. Because you see something living, something nice, something live, not a cold, sterile room, right? And so if you do a little search, right, you can find research articles published in different things. So there's the Horticultural Science is a journal, right? And so there's a research therapeutic influences of plants in hospital recovery rooms. Right? So instead of having get a picture, right? Instead of having a room with nothing living in there, versus this one has a few plants in there. But some effort to maintain plants. You got to water them. Having dead plants in a room is no good. Right? There's some debris and things, but does it make people feel better? Does it help them recover? Right? And so this was an experiment. They go into saying things about the people. There's human research protocols. This study was done in Korea, where there was research review boards that judged whether it was safe. Is this going to influence people too much? Patients were randomly assigned to either a control or plant room as they became available. They had single-person rooms or six-patient rooms, so you were a group of people. So they had that factor. The patient views from the hospital windows were kind of similar in the rooms that they used, because if the one group had a view of the forest out in the distance and the other one didn't, that would make it kind of unequal. So it was kind of equal. 19 to 60 years old. And there's a few other reasons why people would not be included, because if they had some infection or weak immune system, maybe they shouldn't be around certain types of insects and things like that. But so they did this experiment, randomized to get two groups. It wasn't a matched study. They measured how much analgesics people are taking in. There's one group taking more painkillers versus the other. They had pain intensity, pain distress, anxiety and fatigue, some state trait anxiety inventory form for control and plant groups, for females doing certain types of surgeries. They did surveys after the fact, before, after, what do they think of the room, what do they think of their experience, and they come up with a conclusion that generally there's some advantages to having a living thing there. It makes it a nicer experience in general. So it's it would be a fairly, big expense, a commitment to have growing plants in there, and so it's trying to demonstrate that maybe it's a good thing. If you Google on the web, there's an organization called Plants for Patients that thinks that, so it could be, they create another group that wants animals in the hospitals or art in the hospitals or things to make it a better experience. So you can do research on these things, and little bits get done here and there, different groups, different contexts to kind of maybe push toward a general conclusion that making making the experiences more humane and inviting and life affirming in some way, right, will produce noticeable actual benefits in how people respond. People respond, after all, not only based on the physical things, but their mind, attitude, spirit, and everything kind of goes together, right? So it's part of the placebo effect, right? But so it's somewhat real. It's real in some ways. And so anyway, that's so it's kind of interesting that shows up was kind of similar. But today we want to look at two independent samples. So this area here is that we get a group 1 and a group 2. Right? This could be a randomized experiment. It could be just other two groups that exist out in the world. The people that sign up for something, that don't sign up for something. It could be male, female. It could be based on your year or your first year now versus first year 3 years ago in college. And in group 1, there's a sample size. In group 2, there's a sample size. Thinking about quantitative measurements, body mass index, blood pressure, dollars, returns, or something like that. And so we can kind of compute an average in that group and an average in this group. We also have a standard deviation of measurements in this. This is all based on the sample statistics. Sample values, sample statistics here. But what we're interested in, the parameters. The parameters are the mean in the first group and the mean in the second group. Parameters. Primarily. And we're going to be interested in the difference, right, between the two groups. Depending on the context, you might redefine which is the first and second group. That's kind of arbitrary. You're taking a difference one way or the other. And you're interested, is one less than the other? What's the magnitude of this difference? The estimate that we're going to use is pretty straightforward. Right? Of this difference, it's just the average of the first sample mean minus the second sample mean. And based on that, we're either going to do a confidence interval or a hypothesis test to get some statistical inference about this difference. We're going to see some difference in the sample, but how well is that estimated? Right? Is it estimated very precisely? Is it really different from 0? Right? So we need the standard error of x bar 1 minus x bar 2, and we need a distribution t-squares, right? So if we reach back to some of the probability work, we can figure out a little bit more about this standard error. So if there's the variance of x bar 1 minus x bar 2 can be written as the variance of x bar 1 plus the variance of x bar 2. Things inside of variances get squared. It's a square deviation. Technically, there's another part here, a covariance that would apply if x1 and x2 tended to go together. However, in this case, because of independent samples, not paired samples, right, that covariance is 0. So we just have the variance of the first average plus the variance of the second average. And mathematically, probability theory, the variance of these two things add together. Right? And the variance of this first one of x bar 1 is sigma 1 squared over n1, and this one is sigma 2 squared over n2, where these are the population variances. So the question becomes how to estimate that. One estimate, one way to estimate that variance would just be put the S1, but put the two variances in here and divide by their standard errors. That's fine. That's one way that it's done. But what I think is preferable is, if you're studying two groups and the standard deviations are about the same, it's reasonable to treat them as the same. So this one is okay, and it's done in times, and you'll see the formulas there. But if the two variants, what we'll say here, I'm just thinking about how to put this all on the page. If these two things are equal to some value of sigma, then we should combine the information from both groups to estimate the variance. And this combination process is usually referred to as pooling, to pool or combine the estimates of the variance. We have two variances. If they're really the same, we only need to estimate one time. So let's put these two things together. And so the pooled estimate of that is going to be an average of the two variances. Yes?
Is that sigma 1 or a sigma comma?
This is a sigma 1 from the first group.
Okay.
And this is a comma.
Comma, okay.
Yeah. So this is just some kind of common value, whatever it is. Be the same in both groups. So the pooled version of S squared either has a P here, or you can write pooled down there. The pooled version is, we have the first group and we have the second group. We're going to combine those, and we're going to weight them by their degrees of freedom. Multiply it by the degrees of freedom, n1 minus 1. This one gives n2 minus 1, because you might have different sample sizes, and divide by the total, n1 plus n2 minus 2. n1 minus 1 plus n2 minus 1 is our n1 plus n2 minus 2. So that's our kind of common estimate of the variance. So using that, this value, our estimate of the variance of x bar 1 minus x bar 2 is going to be this pooled variance. And it's divided by n1 in the first group. And it's divided by n2 in the second group. So instead of s1 squared over n1 plus s2 squared over n1, we have the pooled one for both of those. We get better information on that variance by putting the two samples together. So this, what we call our standard error, is going to be the square root of all that. The square root of all that can be written as s pooled times the square root. Take the square root of this whole thing up here. Take the square root of that part, and you take the square root of that part. So the common estimate of the standard deviation is pooled S times something like sample size. Something related to sample size. Square root of 1 over n1 plus 1 over n2. And that's our standard error. Then we're going to make a confidence interval hypothesis test using a t-distribution like we've done before. There's a little bit more motivation where that comes from. Two samples, we get two sample sizes, two means, two standard deviations, and we do something with that.
So that equation, the n1 minus 1, like the s up there,
Yeah.
that's a common estimate of sigma squared, you're saying?
Yeah.
And would it be the same for the variance of both x bar 1 and x bar 2?
Mhm.
Like the same thing?
Yes. So instead of having a separate sigma 1 squared and a separate sigma 2 squared estimated by these two things separately, if that parameter, if that unknown thing, that unknown variance is really the same, and our data is kind of equally spread out in both groups, around the different means. And we put them together and we just use that one estimate. So we can do a confidence interval for the difference. We're going to put it at x bar 1 minus x bar 2. And that's our estimate. Plus or minus, it's going to end up being a t-value. Right, these are quantitative measures like we had before, times the standard error. And so x bar 1 minus x bar 2 plus or minus our t-value. And the thing we use for the standard error is that pooled standard deviation times 1 over n1 plus 1 over n2. But to finish this, we need a degrees of freedom. We need a particular t. So the degrees of freedom that we get to use then is n1 plus 1, minus 1, plus the n2 minus 1, which is the sum of the two sample sizes minus 2. We reduce the sum of the sample sizes by 1 for the first mean. We're estimating a second mean, so that also gets subtracted. So it goes down. Now in terms of probability theory, that we get to use this particular degrees of freedom, it actually ends up being the right thing to do because we've pooled and there's a common one. If they're not, then things go a little bit funny and there's not actually, it's kind of a classic problem, and there's not an exact solution, but there's approximations that get done in practice. This one works out nice because you don't have to do that approximation. You get to use a larger degrees of freedom, which is good, right? Because you get smaller t-values and so on. Let's look at an example. So let's say you are looking at lung vital capacity, forced respiratory volume, measures how much air you can blow into a machine, that measures the stream of blowing out. And let's say you have a group of brass players, right? The trumpet, horn, or tuba or something, trombone, something like that. And the other control group, probably similar in age and generally healthy, so that it's kind of a fair comparison, other than one plays a wind instrument. And maybe this is a small sample size, 8 and 7 for this, and for the average in this group is 4.83. The average in this group is 4.74. The standard deviation reported in this group of the several measurements is 0.435 and 0.351. So if we want to do, say, 95% confidence interval for the difference, so mu1 minus mu2, what does that represent? This is the difference in average lung vital capacity. Comparing the brass players minus the control individuals. So our estimate is x bar 1 minus x bar 2, 4.83 minus 4.74, 0.09. If this is in like liters of air, I think this is the measurement unit. The liters there. I mean, that doesn't look too big, right, in this one sample. But in statistics, we would still ask the question, is it statistically significant? Right? Because even if you have a small difference, if there's small standard deviations or large samples, you can still say that this is different from 0 or significant, or you still express how accurately this is. Right? Is it plus or minus 0.1, plus or minus 0.2, and we're still interested. So we're going to make a confidence interval about this. We need to do a couple of things, right, to get this done. Right? A couple extra steps, right? So degrees of freedom is one step, right? N1 plus N2 minus 2. So 8 plus 7 minus 2 is 13. We're going to do 95% confidence interval. So we're going to look up a T value with 13 degrees of freedom. And we look at the 0.025, what is Brosnan for tonight? 0.975. Column, right? So we want 95% in the middle. There's 2.5% down here. So you add those two things together. And so you're looking at the 0.975 column to get that t-value you need to use, right? And so that t-value, 13 is on there. So here at 13, we use 2.16. A little bit bigger than 1.96, right? Because we only have such a small sample size. So we're looking at this 975 column gives my 95% assumption, and across it's 13 degrees of freedom, and get that one. T 2.160. But we need that standard error, right? We need that pooled one. So there's that step. S pooled. I have the square written down, right? So we had 0.435 is the standard deviation, so that's just an S1. So we have to square that. And the other one was 0.351 to square that. We multiply it by the degrees of freedom from one sample, so 8 minus 1. This one gets multiplied by 7 minus 1, because there was one less person there. And then we have those two things together to get that. My notes say that's 0.1628. The square root of that is about 0.4. Because 0.4 squared is 0.16. So that's about this, the S pool. The square root of this 0.1628. About 0.4. It wouldn't be exactly 0.4, but it's pretty close, right? So you can kind of check initially that you get something reasonable. Right? If one standard deviation is 0.435, the other standard deviation is 0.351, this pooled one should be in between the two. So if you got some number that was vastly different, then something would be off using the calculator or the formula. So that's the pooled. Standard error formula is that pooled number times 1 over the sample size, the first one, which is 8, and 1 over 7. And so it's 0.236. Right, so we have enough, the elements that we need, right? We have our average difference on the other page. We have our t-value, our standard error. Right? So our 95% confidence interval is 0.09 plus or minus 0.16. That standard error 236 there gives us some number. Tell them to start R, so we'll do a few calculations. Does anybody want to see the previous page and see any of the numbers, or smaller too? So the confidence interval, which is 0.09 minus 2.16 times the standard error, up to that plus. So about negative 0.42. Negative 0.42 up to about 0.6. So that's a 95% confidence interval. So what does this confidence interval tell us? Does there appear to be a substantial difference, a significant difference between these two groups? This is pretty wide, it includes 0. Seems like there's no real evidence of any difference. The 0.09 liters is not that much, right? So the average difference wasn't that great, and the standard error is a lot bigger. The other way we do is a hypothesis test. With this, once we have the preliminary work, all of this, right? Degrees of freedom, probably getting a cutoff value, a reference value, the pooled standard deviation, and the standard error, it's all the same. But out of that, our hypothesis, the null hypothesis, again, always the same, no change, no difference, so that the average of the two groups is the same. Sometimes we do it one-sided, but you can also do it two-sided. There is some difference. This one there is an average difference. So our t statistic is, or an estimate. Well, technically, we subtract 0 because the difference is 0 here. In some circumstances, you could think that there was an actual difference that you'd be interested in. And then you would put that, how the difference should be 1 liter, then you would put 1 here. That was the null hypothesis. Ours is 0 in this case, divided by standard error. So 0.09 and divided by the 20.236 is about 0.25. A quarter of a standard error. That's not very extreme, right? It's easy to happen. Fairly regular variation about the mean. Degrees of freedom was 13. The T975 value for that one was a 2.16. And that's a lot closer to 0 than our cutoff value. So do not reject. It is plausible that there's no difference between these groups based on these data. But any points?
Can you just go over again why we would reject the hypothesis?
So in this case, we don't.
Oh, that's right.
Yeah, we don't reject. We don't reject because this was our t statistic. The t statistic is not extreme. It's not out in the tail of the distribution. So in this case, you could say do not reject H0 because our t statistic, which is about 0.25, is less than the t distribution cutoff. At 2.160. So the t distribution centered here at 0 is t with 13. If we end up out here, if we end up, this is where we reject out here. We would reject out here. And our statistic is about, about right here in the middle. 0.25 rather than 2.196 or negative 2.16. So if we had a big t statistic, we reject, it's close to 0, then our estimate, this 0.09 is within it's only a quarter of a standard error of the center. And so it's not unusual.
Could you go back the last page?
Yeah. So this one. So we got our confidence interval, our hypothesis test. You only need to really do one of these things, either a confidence interval or hypothesis test, right, to answer the question, are they different or not? Right? Because hypothesis tests don't reject 0, confidence interval includes 0, so 0 is not not unusual. Confidence interval, I think, tells you a little bit more. You see the range of likely values, a little more information.
So since it includes 0 in the range
And
of
this-
like between -0.42 to 0.6, it includes 0 in the range, so you can say that there's no difference.
Right. So 0. So based on this, you can say 0 difference is plausible, is believable. Because that interval includes 0. Anything in there might be the truth. We generally think it's closer to 0.09. 0 is pretty close to that. That would be consistent. Right. How about one more? Example. So with tonsillectomies, they're removing the tonsils, infection, or other reasons. Conventional surgery is one option. There's another surgical procedure called coblation. That does things with selective numbing and I think I'm not a surgeon, so I don't know exactly. It was just an alternative way of approaching it. Two groups are randomized to get one or the other. 47 had the conventional, 52 had the coblation method, the average pain score. So pain scores, you could ask the patients on a 10-point scale or to indicate versus some graphical means or something about how much pain they're in. The average was 4.3, here it was 1.9. The standard deviation of the measurements was 2.8 in this case and 1.8 over here. And does this alternative surgical approach reduce pain on average? It certainly looks promising, right? X bar 1 minus X bar 2, in this case, 4.3 minus 1.9, 2.4. So if that's on a 10-point scale, that seems like a pretty important reduction. Like that article on the plants, they reported how many analgesics, how many painkillers and so on did people take, right? So if somebody's in the surgery for, in follow-up for 12 hours or 24 hours after surgery, I don't know if they do that inpatient anymore, right? Maybe it's all outpatient now, but so they may have to gather information. Did you take Advil or whatever in the 1 hour after, the 3 hours after, the 6 hours after? How much did you take? Somehow gather that information about what they're taking. Instead of a pain score, it could be an amount. All of these we're going to pool. The pooled value, if you calculate, that is 2.33. So that pooled one, you would take the square root of, so there were 47 in the first group, so 47 minus 1. You take the 2.8 squared, 52 minus 1, 1.8 squared, and then add these two sample sizes minus 2 down there, and that should give you this pooled value. The pooled value should be between the two. It won't necessarily be exactly halfway, but it's between the two. Now we can either do a confidence interval or hypothesis test. Well, either way, we're going to want to think about degrees of freedom. N1 equals to 2 minus 2. So 47 plus 52 minus 2 is 97. If we want to do a 95% confidence interval, or we want to do a level alpha 0.05 test, we're going to look at a t-value with that 97 degrees of freedom and that 975 column. There. So we'll return to that, but let's look at the key table. So under that column, there, our table doesn't exactly give us that, right? 97 is in here. And then this one, right, that's the values for 60 and 120. It's at 2 or 198, 1.98. If you use 1.99, that's going to be close enough. You could use 2 if you wanted to be conservative, but 1.99 is going to be accurate enough. So that value is 1.99. So we have our average difference. We have our pool, standard deviation, and sample sizes, so we can get standard error. And we have a kind of a T reference. Right, so confidence interval, 95% confidence interval for average difference in change. X bar 1 minus X bar 2 plus or minus our T value times standard error. So this average difference was 2.4. This was about 1.99. Our standard error was that pool value of 2.33. And we screw 1 over 47 plus 1 over 2. Right, that's the standard error. And this thing ends up being 1.47 up to 3.33. So that's a 95% confidence for where that interval, that average difference is. Put any questions? Go ahead and write it down. Think about it. If I do a hypothesis test, is what type of T value am I going to get? Is the T statistic going to be close to 0? Is it going to be large? What type of T statistic value will I get? The null hypothesis is that they're equal. The difference is 0. Right? Is 0 reasonable? No. It's a long way from 0. Right? So I have to get a T statistic that's pretty big. I need something over 2. Right? So 0 not the confidence interval. So T statistic must be large. And in fact, the T statistic is very large. The T statistic, the average difference was 2.4. The standard error, I don't know if I have that written down, but it's this thing, 2.33 square root of 1 over 57, 1 over 52. Ends up being about 5.12. A lot bigger than 1.99.
What was the full equation for T stat?
The T statistic, this one, the equation, you take the estimate, the differences, right there. Here's the pool, standard deviation. And instead of just dividing by the square root of n, we have 2 n's. One and 2. Those get added together, the square root of that sum.
Okay, yeah.
So instead of just s over 1 square root of n, you have the two in there and they get added together. So it looks a little bit different, right? But it's not the same. That's the t-statistic. The pooled values is 2.33, the two sample sizes. The standard error is about 0.05 or a little bit less. And so the t-statistic is very large. So we reject the hypothesis, null hypothesis. There is a difference in this. It does seem to make it probably worth training the next generation of physicians who are going to be doing tonsillectomies to do a variation in the procedure. Right, so there's an example on the handout. It's another example, just to write some more things down. You have one more comparison. You have 36 dog owners volunteered for a study. You monitor them, for a month. How much, on average, are you walking per day? Maybe this is not only the time that they're walking the dog, but maybe the time that they're going to the store, just walking throughout their day, or walking to work or school or something. So those 36 measurements have an average of 42 and a standard deviation of 1.7. And there's 28 cat owners. They walk on average 3.1 and a standard deviation of 1.5. So do dog owners seem to walk more? It's not asking them to answer the question, do they do more exercise, or are they healthier or anything. It's just, you could give people a pedometer to wear, or a Fitbit or something that would track them. Now it's a lot easier than it used to be with technology. So the difference is about 0.9 miles, so that would seem to be a pretty sizable amount. Is it statistically significant? Are we sure it's different from 0? So we'd have to pool the standard deviations there. We get 1.62. That's between the 1.5 and 1.7 for each group, so that's good. That's what it should be. Degrees of freedom, we get 62 because we added two sample sizes together. The t value is almost 2. If you look at it on a computer, it's a little bit 1.999. The difference actually is 1.1 miles. I subtracted wrong here. So if you do a 95% confidence interval, you get 2.8 miles up to 1.82. And so that's above 0. Right? So it looks like they're significantly different. If you did the symbol there, the mu sub d is the difference between the two means. Mu1 minus mu2 is the difference, 0. And the t statistic is 2.695. So again, that's bigger than 2, bigger than that 1.999. So we would reject if you did it that way. So that's essentially the mechanics, right? It's an interpretation and set up this, right? There's two little wrinkles to mention. Right? So we've done the pooled version. I recommend that one. If it makes the most sense to me, conceptually. If you're testing the means between groups, there's other stuff going on, like one group has big outliers, or another one's really skew, or has huge variance compared to the other one, then there's kind of more issues going on. So if the variances in the samples are a magnitude of 2 or 3 or 4 above each other, you might not want to pool, but then again, you might not want to test the means anyway. Right? So we pooled when we assume those two variances. There's versions where we would do, so in this case, the standard error thing that we would calculate would be the pooled standard deviation, and 1 over n1 plus 1 over n2, square root of all that. Another way of writing this thing is, if you bring the pooled thing inside, it gets squared. And it's just replacing the two sample standard deviations with that common estimate of that one parameter. Estimating one thing instead of 2 is easier. Unpooled, if you don't make that assumption and allow each group to have separate standard deviations, you'll see in the book and other things that a standard error, you just take each group separately. And you could do it like that. And it would seem to save you the effort of pooling it and save you that one step. But if you have to estimate two things instead of one, that's harder work. You're using the data to do more things, and there's more uncertainty. There's more of a chance that one of those, S's here could be kind of haywire, very large, very small, and that will cause things to blow up a little bit. Right? A little easier. The other thing that it ends up doing is the degrees of freedom for the T procedure aren't exactly determined. Right? There's ways that it does it in the computer. There's ways that it will do it, suggests you do it, but there's not an exact solution. So they either it, you use a conservative approach, and say the degrees of freedom is the smaller minimum of the two individual ones. Be pretty conservative. Take the smaller of the two that you would use just for a one sample problem, or use some sort of approximation. The book gives the formula. It's a little bit more complex. We don't need to calculate it. I think you need to use a conservative one, or you do pooling. The approximation, a statistician called Welch, somebody else named Satterthwaite. That did these numerical approximations to the distribution. Right? So in the probability theory, in mathematical statistics, you can figure out what would work. Well, it's just going to give you different degrees of freedom, right? and give you different numbers. And many times, whether you pool or not, if there's really a big difference between the groups, you get significant results. Right? They go together. If there's no effect, if there's really no difference between the groups, either one you do probably is not going to show a significant result. But there's some point in the middle where it's kind of on the boundary of significance, where pooling or not pooling will make a little bit of difference. Conceptually, again, I think it makes most sense to pool. That would be I think the best one to do. To show you kind of how this gets done in R, we could enter a little bit of data. And so in one of those, come back, would like to shut down? Right. I guess it did shut down. Going back to that first example, right? So if we enter a little bit of data, the brass players, or a subset of them, I don't have, say there's 4.7 for one person, and 4.6, and 4.3, and 4.5, and 5.5, and 4.9, and 5.3. These numbers match the average we had before. It's actually a little bit shorter. There's just 7 instead of 8. I had to look back and figure out what happened with my sample sizes, but in any case. And in the control group, if their data looked like this, 5.1, 4.7, 5.0, we would have the brass players and their scores, and then the control group and their scores. There's only 5 of them, so that's a little bit less, the length of the control group. It's just 5. In R, there's a command called t.test. T.test. And if you put brass in here and control, it'll do a 2-sample t-test comparing those. And it's not assuming it does this Welch approximation. It gives the degrees of freedom as a decimal. It's a more complicated formula. But it uses that instead of the pooled one as a default. Right? We get the estimate of the two means. It gives you a 95% confidence interval. It's about the same as we had before, about -0.42, about 0.6. It gives you a t statistic. Our t statistic was about 0.25, so it's a little bit less. But still, this one's pretty small. The p-value, right, is 0.7. It's not below 0.05. It's not significant. Everything's consistent with what we've done. Right? But it's used this particular thing called a Welch 2-sample t-test. And you probably Google, Welch 2-sample test. Wikipedia page with unequal variance t-test. If you do this one, it uses this formula to find degrees of freedom. So instead of doing our simple formula in 1 plus n2 minus 2, it does that one. So numerical examples there. There's other ones that, Sat Earthquake is somebody else that did this one. We're not focusing on so much the details of that alternate testing procedures. We want the bigger picture. That if there's a difference, you're going to compare it to the standard error, and then compare that to a distribution. You could make it do it with equal variance. There's an option, var.equal. Make that true or just a t. Then it does the ordinary 2-sample t-test. In this case, I had 7 in one group and 5, so that's 12. So when I subtract 2, I get 10. And the results, the averages are the same. Confidence intervals only slightly change. The p-value, the test statistics, just slight changes. It doesn't make much difference in this case. The 2 standard deviations are pretty close together. So sometimes you look at something and maybe if you try to reproduce exactly what's in an article, they might have used unequal variances or equal variances, and so it will change the results a little bit if you're trying to actually reproduce what's there. The last thing to talk about really is, should you do a 2-sample test or should you do paired, which is better for design, which will give you more accurate results. How do you know, for example, in the dog owner and pet owner one? So how do we know? We have 2 independent samples. Versus paired data. Imagine this. In the case of the dog and the cat owners, what would be one clue?
The 2 independent variables.
Yeah, so if it describes it as we have this one sample of the cat people and one sample of the dog people, if it describes it, it's going to describe it as 2 independent samples or 2 different groups. Right? But I mean, you could do pairing, right? You could take one say apartment building and find one person to participate in the building that owns a cat and one person that owns a dog, and they're living in the same building. Right? If that building is close to trails, maybe they go walking on those trails. Or if it's an urban area, maybe they both walk to work, right, or walk to the grocery store, right? So if they're at the same location and matched like that, then you have a dog, the distance for the dog person, the distance for the cat person. So it could be paired. If you live out in a rural area as well, right, and you have 2 people that live on kind of the same road in the rural county, their situation in terms of walking, maybe they have a little more land, but maybe there's no sidewalks along the street. So you could do it paired. How would anything change? Right? So in this, it's paired. Right? You have 2 sample sizes, but they're always the same. In the paired data, you have your first measurement and your second measurement. It's always on pairs. So somehow it's paired. It's the same person, or for each person in one group, you get another person in the other group, and it's exactly matched up. Right? So pairs, right, this whole big picture over here, would be pairs. If it's independent samples, but you can have N1 and N2 being different. You don't have to have the same sample sizes. For efficiency, sometimes it's good to have the equal sample sizes. But sometimes it's more expensive to get one group versus the other, or It's just natural groups that are occurring in your general population, general sample. There's no guarantee they're going to be equal, right? If it's not equal, then you don't have the pairing. But if it's not, even if you had equal sample sizes, 100 people with dogs, 100 people with cats, there's something in the description of the problem. You can't get away from the description of the problem. Right? You pick these 100 people, these other 100 people randomly from populations, and they're not matched up. But otherwise, in the matched pairs, there's some clear indication that it's that. When is it good to, so say we're planning a study and we're going to take N individuals in one group and take 2 N measurements. Should I use a matched pairs design? Or not? If it's not, then you just have these two samples. One to N over here and one to N over here. If it's matched pairs, you split people into groups 1 and 2, and you take both measurements and they're paired, and the next group is paired, and over here you take the difference. Right, so x1 minus x2. So here you end up with N differences. And over here you end up with x bar 1 minus x bar 2. And so there's really 2 N measurements that continue through that process. Is it good to do matching if you can? It's a complicated question, and in some ways, but very fundamental to how you would set up design. An advantage we got over here is correlation. If you could set it up so that the first person and the second person, the first and second measurement in a pair, these are highly correlated, then the differences can be very, very small. There's a high correlation that you can get in there. Then, based on only N observations, can be better than 2N, as long as you can get a very high correlation. So, if I call this X and Y, here, take the differences. If X and Y are highly correlated, then doing the match study, then matching can be better. Although it implies you only get in observations instead of 2N, that decrease in correlation, the decrease in the standard deviation, can give you ultimately a standard error that's much smaller, and it can be better. So in any study, even with animals, walkers, dog walkers, if there's a big effect on the environment or people's ages or male, female, or whatever, you can determine based on your sample and the people you recruit if you can match, and based on those characteristics, it's highly related to the outcome, the health outcome. It's good to match. If it's very difficult to do, or you really can't operationalize that, right? You just need volunteers to come in. You're not actually going to know where they live and be able to match them up so well. You might just, for practical points, have 2 independent samples. Then you might still do well with large enough samples, but if you can match, you often can get a big advantage. So. But anyway, that's our 2 samples. Are there any? We don't have too much time left. We've got 5 minutes left, but were there any questions about homework? Yeah.
When would the independent sampling be better?
When would the independent sampling? So if there's a kind of a weak correlation between these, if it's if it's not that highly related to 2 measurements, or if it costs a lot of money, if it was very difficult to do that, There might be a practical side that you could just say bigger samples in these two groups rather than do that expense of following people all, up and figuring out, so it's kind of weaker, right? If you ask people how they're feeling, more and more qualitative aspects of how things are going, those things from one time to the next might be weaker correlated than their blood pressure. Okay. See you on Friday, and we'll talk about the exam, and talk about the total formulas and all that.
I should do that too, actually.
Bye.
Breath Finley. Cheers.
Have a good one.
Yep.
All right.
Thank you.